everyone. We're going to have Jerry Lee talking about lower bound for robust estimation. Thank you.
All right, cool. Thanks. So this talk is about I don't know, a pretty interesting direction. I'm not gonna lie, some of the results are sort of I put it towards there for a reason, it's sort of not super satisfying, but I think the direction is really nice, and I think the connection we draw, at least to me, feels supernatural. So hopefully there's something more that smarter people can figure out. Okay, so this talk is about the following basic problem in statistics: is robust mean estimation. Is the following problem. So let D be a distribution over R little d, and then instead of getting samples from D, we get a corrupted set of samples from D. And what does that mean? We say that a set of samples is epsilon corrupted from D if it was generated via the following process. First, you sample n samples ID from this distribution D, but then you give them to an adversary, and then they get to inspect and change an epsilon fraction of these samples however they want. And then the resulting samples are sort of returned to you in some arbitrary order. Okay. The robust mean estimation problem is a very well-studied problem, dating back to sort of statistics in the 60s or whatever. And just given an epsilon corrupted set of samples from this distribution D, recover the mean of this distribution as well as you can. Okay, so this is the basic question that we're going to be considering in this talk. Any questions so far? Okay. So it should be clear that without additional assumptions, that this problem is completely impossible. I need some regularity assumptions on my distribution D. So what are the sorts of assumptions that you make? One class of standard assumptions you make is a bounded moment control on my distribution D. Okay. And the reason why this is nice for this problem is because of the following fact, which is kind of relatively easy to prove. If I have a univariate distribution with mean mu and bounded central kth moments, so let's say all the moments up to degree k are bounded by at most one. Then if I have a sufficiently large set of corrupted samples for my distribution, there's some relatively easy to compute estimator. You just take the truncated mean, which achieves error, which is O of epsilon to the 1 minus 1 over k. Okay, and this is tight. So this is information theoretically tight in one dimension. Okay, so this is sort of the rate that you might expect, 1 epsilon to the 1 minus 1 over k. In particular, if I bounded covariance, this corresponds to k being 2. So then my error here is epsilon to the 1/2. Okay. And it turns out that this is not only true in sort of one dimension, but also true in higher dimensions as well. So this exact same statement with just some things changed to it. So yeah.
Where can I find this fact? Does this go back to the 60s? Folklore,
I guess is what you would call it. I think you can just sort of what you just do is simply you truncate the epsilon tails, the largest and smallest, and you just do the computation, and it's a couple lines. It's in some lecture notes somewhere, I'm sure.
Or by my book.
Or by his book. Yeah. Yeah, hopefully, yeah. Anyways, okay, so if I have a d-dimensional distribution, and I have bounded central kth moments in every direction, which is, so if I take any univariate projection of my distribution, and I compute the central kth moment in that direction, this is bounded by 1. Then, given an epsilon corrupted set of samples, I can achieve L2 error to my mean, to the true mean, with some inefficient estimator that also achieves error epsilon to 1 minus 1 over k. And crucially, this is the difference between the univariate and the high dimensional settings. The univariate estimator is just this truncated mean. It's very easy to compute. This estimator is not necessarily, or it's not a priori sort of efficient. Okay, but from an information theoretic standpoint, this is still the truth. Okay. So this is one sort of common assumption. There's another sort of more recently introduced assumption, which is directly sort of motivated by this problem of robust mean estimation, and it's this assumption called resilience, which was first introduced by this paper in 2017 by Steinhardt, Charkar, and Valiant. And they say a distribution D is sigma epsilon resilient if for any probability event E that occurs with probability at least 1 minus epsilon under my distribution D, then the conditional mean condition on this fairly likely event is pretty close to the true mean of the distribution. It's at most sigma far in L2. Okay, and you can sort of guess. I mean, this is directly catered towards sort of robust mean estimation with these parameters. There's sort of, it's not so hard to see a connection between these two, between this assumption and robust mean estimation. And in some sense, this is a weaker assumption than bounded moments because just by like, Markov inequality, bounded moments imply resilience sort of at every scale. So notice resilience here only applies for like, two parameters, sigma and epsilon. Like it's fixed for these two parameters. But bounded moments say that, if I have bounded kth moments, then for all epsilon sufficiently small at least, it is epsilon to the 1 minus 1 over k, comma epsilon resilient. Okay. So sort of resilience is like at a very fixed scale. Like I have sort of this control. Bounded moments implies sort of this resilience for all epsilon, like even in like the far tails. Okay. But the main fact that was also proven in the same paper, which is that if I have, epsilon corrupted set of samples from a sigma epsilon resilient distribution, then I can achieve error, which is order sigma. And again, if you plug in sort of this result for the sigma, you recover also the same result for bounded moments. So hopefully these two assumptions make sense. Oh yeah, and this again is computationally inefficient. It's like it's some sort of brute force search over like all subsets and stuff like this. Cool. So right, so far I've only talked about inefficient algorithms, just like completely information theoretic. But what if I care about runtime now? Then for this specific setting, the actual results are quite limited. In particular, sort of we only have results for the bounded second moment setting. And what do I mean by this? So there's this result by Dick, Nicholas, Kane, Kamath, myself, Moitra, Stewart in 2017 that says that if you have two bounded moments, so if you have bounded covariance, then there is indeed an efficient algorithm which achieves error root epsilon, which is epsilon to 1 minus 1 over k when k is equal to 2. So this sort of matches the information theoretic bounds when k is equal to 2. Similarly, if you have an assumption on resilience, which is sort of corresponds to the bounded second moment assumption, so this is sort of like epsilon to 1/2 versus epsilon, you can almost match sort of the information theoretic weights in that setting up to this root log factor. Okay. And then like, that's it. In some sense, like if all we want to make are these sorts of assumptions, like bounded moments and nothing else, then these are like the only results we have. Like, if only want to assume like upper bounds on the moments, this is sort of it. Which is kind of surprising because there's a lot of work in this area. Of course, there's a lot of results in sort of restricted cases with additional assumptions. So in particular, if you have bounded k moments, and the fact that you have bounded kth moments in every direction has some sort of SOS proof, then you can show, this is like based on some joint work with Sam and also by Kuthari, Steinhardt, Stoyer, that you can achieve sort of this error epsilon to the 1 minus 1 over k in at least polytime when k is constant. Okay. I believe you can actually improve this k squared to a k now, but additionally, you can also prove in sort of earlier works, if you have sub-Gaussian moments, so if you have like lots of bounded moments and you have known variance, so say the variance's identity, then you can achieve error, which is like epsilon to root log, almost like nearly epsilon error in polytime. And this wasn't written down anywhere as far as I can tell, but like sort of the same result, I think it was written down in your book for the first time, is that if you have bounded kth moments and also the same assumption of known variance, so if you like know the variance exactly, not just like upper bounds on it, you can also achieve this epsilon to the 1 minus 1 over k. Quality time, but sort of all these things have some caveats. Like you need just some additional algebraic structure on your distribution to achieve these results. So if all you want to assume, and this is sort of weird, right? Because like statistically, all I really need is sort of concentration properties. But these two things at least say I need some sort of anti-concentration in some sense. And this also requires some like additional algebraic structure, which is not like statistically necessary. So somehow there's like something weird going on here that like I really need something, it seems, additional to like do something beyond root epsilon for this setting. Any questions?
The known variance is the covariance matrix.
Yeah, like the covariance. I tell you what the covariance is. Okay, so let me tell you sort of morally why we might suspect there are like really genuinely barriers to this problem. The algorithms for sort of second moments rely on something that all people, Alexander Madry sort of coined this term spectral signatures, which is sort of stuck at least for me, which is basically the following fact. If mu hat is the empirical mean of the corrupted data set, and if this distribution has bounded second moments in all directions, And suppose the empirical mean is far from the true mean of my distribution mu. In particular, it is like little omega root epsilon away. Then if I let V be the top eigenvector of the empirical covariance, I can think of as the optimizer of this quadratic form over my samples. There should be a max here, my bad. Then you have this following property, which is that if I sort of take the quadratic form in this direction and I project all the points, sort of the sum of this, the contribution to the quadratic form from the bad points is like much bigger. This 2 is like arbitrary. This could be like 100 or 1,000, depending on if you care about constants. The sum of the contributions to the quadratic form from the bad points is like much bigger than the sum of the contribution from the good points. Which you should think of as this is very suspicious because like this is a small set, this is a big set. So somehow like even though this is a very small set, they're contributing a lot to the variance in this direction. And this is sort of allows you to make algorithmic progress because all these things are efficiently computable. In particular, I compute the top eigenvector very efficiently. And it turns out you can do the same thing when k is higher. The problem is that instead of having a quadratic optimization problem like this sort of degree 2 thing, I just need to take kth moments. And here, this is like where you get into like the land of like computational intractability. So in particular, you have the following correspondence. Suppose I bounded kth moments in every direction. And now let's make a weaker assumption on like how far are these things. Let's assume it's like little omega of epsilon to the 1 minus 1 over k, which is like sort of the error we're going for. Then what I can do is I can take V to be the maximizer of like the 2 to k norm. So I just take V to be the maximizer of this degree k polynomial over my samples. And if I do so, I get more or less the same thing when I raise things to the kth powers. Okay, so in other words, the optimizer of this 2 to k norm of my empirical covariance gives you a direction where the outliers are large on average. And so all that remains is sort of compute these things. But this is a tensor optimization problem, and these things are hard. And this is sort of like the fundamental sort of idea of like why there might be like real issues with doing this. That makes sense? Okay. It's probably hard. And sort of this is like why one might suspect there are sort of real barriers to this problem. Assuming sort of that you think that this is the only thing you can do, which is in some sense, our methods are like ways to try to convince you that maybe this is like the only thing you can do. This is sort of an interesting point as well, because one might ask, given in particular the context of the previous talks, can you do this? Can you prove like sort of SQ hardness for these problems? And the answer is surprisingly no. Like, not only is it like we don't know a proof, but in fact there is an SQ algorithm, and this is sort of like a fact that typically doesn't come up very much in sort of SQ. Usually we think of SQ as like a subclass of efficient algorithms. This is not technically true, because in particular I'm allowed to do inefficient queries after I've done my SQ algorithms. In particular, the hardness for this problem is just like literally computing the maximizer of this 2 to k norm of something I know, right? Literally of the empirical covariance matrix. So I can like literally estimate the kth moment tensor to high accuracy in time d to the order k, and then all I need to do is like I've written down sort of what the monomials are. I know what the coefficients of my polynomial optimization problem should be. I can just like literally solve this problem, like because SQ doesn't care about sort of that runtime. So in fact, for this problem, there is like an efficient SQ algorithm. So in other words, like if we're going to look for like hardness, we sort of have to rely on other techniques, which is kind of interesting, and also it motivates sort of why we're looking at these other hypotheses, other like sort of reasons for hardness. So let me talk about what we actually did. So the first sort of 2 results are saying that if we're going to go like on using current techniques, like which are relying on sort of finding these like large eigenvectors, or not eigenvectors, but maximizers of like 2 to k norms and resilience things, this is probably hard. So the first theorem is like barely even our theorem. It's really already more or less occurred in this like paper by Barak, Brandau, Harrow, Kellner, Stoyer, Zhao, and we sort of like did it. We more or less sort of give like a refinement of this theorem that says that it's hard to just compute this like maximization problem for k greater than, I guess I should say k greater than like 4 or so. Actually, you can prove this for k anything strictly greater than 2. And yeah. Oh, I mean, so you sort of want sort of like the exact constant of hardness, sort of. This is the reason why you sort of want this c to the k over 2 in general is because like yeah, c is bigger than 1. Yeah. But you know, I stated things for like moments which are bounded by literally 1, but sort of the most natural thing is not just like kth moments are literally 1. It's like the most natural thing is like the kth moment is like looks like the kth moment of a Gaussian, which scales like k to the k over 2. And so you want to say like a multiplicative approximation to that is hard. And sort of that's like why this is sort of. Or in other words, it's saying like a constant factor approximation to like the k to the k norm, like not just like the kth moment, but like the kth moment to the 1 over k. But again, this is nice. In some sense, it's already more or less proof. We also show that under the small set expansion hypothesis, the problem of like certifying a resilient subset is also hard. So given vectors a n, determine if the uniform distribution is over these vectors is like pretty resilient or like far from resilient. And obviously all these parameters are like not like tight. There is asterisk here, which I will explain in a second, hopefully. Okay.
So 0, 0, 1 and 0.4, you see the ratio can become constant.
Yeah, you can take this to be, I mean, so the small set expansion hypothesis, like the qualitative version of it, that you can use sort of, you can sort of vary this constant to like be anything arbitrarily small. But you can take this to be fixed, and you can just like, you know, depending on what you're assuming is hard for SSE, you can make this. Okay. So, yeah.
So that the for make output X compare.
Yeah, in particular, because like I'm showing even like a constant improvement is hard. This presumably shows that doing anything below, you know, little omega root epsilon is like also difficult. Okay, but these are sort of not directly about robust mean estimation. These are sort of like, if I want to solve robust mean estimation, I need new techniques. I can't just like do these things. What would be more interesting is like a direct reduction to sort of directly showing that robust mean estimation is hard. And this is what we sort of do. So what we show is that under a slight variant of the small set expansion hypothesis, the following problem is hard for some parameters alpha and beta. Given vectors b1 through bn in Rd such that there exists a set such that the uniform distribution over this restricted, like slightly smaller set is resilient. The goal of this problem is to output a vector which is close, beta root epsilon close to the empirical mean restricted to the subset. Okay. So why does this demonstrate sort of hardness of like robust mean estimation and resilience? I can take my distribution to simply be like my corrupted distribution. I can take the true distribution to be a uniform distribution over this bi in this set, right? And then I can take the corrupted distribution to be the uniform distribution over literally everything. And then, you know, if I draw enough samples, I'll recover the support exactly. So like I don't really have to worry about sort of like the support or anything, or like samples versus like given a description, sort of everything here is like supported on polynomially many points. And then you can just check, you know, literally this is the robust mean estimation problem for that set of distribution. Like, you know, I want to recover the true mean, which is the true mean of my distribution is literally the average of these BIs. And I'm given samples from something which is epsilon close to it. So this sort of says that, you know, robust mean estimation for under this resilience, you cannot beat sort of a root epsilon even by like constant factors.
By samples, there will be some repeats and stuff, right? It won't be exactly the same.
Yeah, but if I tell you sort of like, if I tell you like the distribution has like n support, which I can, you can just literally just, yeah, you just figure it out. Okay. So this says that even improving upon root epsilon by constants, even if I have some sort of assumption on like, you know, the resilience here, and some improved assumption on the resilience here is probably hard. Okay. I'm probably not going to tell you anything about the techniques, or very little about the techniques given time, but let me tell you at least about something I found kind of curious about the small set expansion hypotheses. You know, emphasis on the C's. Okay. So what is a small set expansion? If I have a regular graph G on n vertices, I can let phi sub G of S for any subset denote the expansion of S. This is simply the probability that a random walk starting in S leaves S in one step. Okay. And then I can define this quantity known as the expansion profile of G, which is simply the minimum expansion of any subset of size delta n. Okay, so this is some function. Now, the original small set expansion hypothesis, which was like first introduced in this paper by Raghavendra, is the following assumption that says that, or hypothesis, that for every constant delta, there's some epsilon such that it is NP hard to determine if phi sub g of epsilon is at least 1 minus delta, or phi sub g of epsilon is at most delta. And for people who are like more familiar with SSE, I'm sorry, I'm switching to constants delta and epsilon, but it's like more convenient for me. Okay, this is like the original, like if you look at the paper of Raghavendra hypothesis of SSE, there's another natural variant of SSE where instead of looking at phi sub g of exactly delta, I look at phi sub g for all delta prime less than delta. So for every constant delta, there's some epsilon greater than 0, such that it's NP hard to determine if phi sub g of epsilon prime is greater than 1 minus delta for all epsilon prime less than epsilon, or if there exists some epsilon prime such that the expansion is pretty bad for that epsilon prime. Okay. So I'm going to call the first one, for obvious reasons, SSE equals, and the other one SSE less than or equal. Okay. Somewhat frustratingly, these are considered like interchangeable in the literature, but as far as I know, they're not. I'm not like an expert on this stuff, but we like asked Prasad, and like he was like, yeah. So like that's some evidence, I guess. In particular, so the original paper of Raghavendra showed some reduction from SSE equals to unique games. So if SSE equals is true, then unique games is hard. Reductions of this form are like not necessarily known for like the other version, and equivalences between these notions are not known. Like this is actually, as far as I know, just not in the literature, and like seems somewhat non-trivial. But they consider these two things to be roughly interchangeable. In particular, you know, this previous paper by, I'm not going to try again, but you know, by the hypercontractivity sum of squares paper, they refer to this less than or equals to as the sum of small set expansion hypothesis. But, and you know, most of the time this seems like not a huge deal. In particular, it seems like it's okay. But so in our setting, it turns out there's like a real distinction between these two problems. In particular, the less than or equal diversions talks about expansion sort of at all scales, less than or equal delta or epsilon, just like how moments are like resilient at all scales for us. And so there seems like there's actually a natural, you know, sort of correspondence for us where like, if you assume the SSE equals, you get some statement about resilience. And if you assume SSE less than or equals, you get something about bounded moments. So when I said like, you know, I had these asterisks previously, I meant that for the resilience one, I meant SSE equals, and for the other one, I meant SSE less than or equals. Okay. Kind of weird, but you know, we'll go with it. I am going to skip this, but this is a really nice sort of like the reason why you might expect. Oh, I can just talk about this very briefly. Okay, so let me tell you sort of at a high level about like what the connection is between sort of small set expansion and like resilience and you know all these things about robustness. This is a technique that we didn't introduce. This is just like a technique that was already considered, but it seems like a very natural connection to our setting. So given a graph G, we let M sub G denote the stochastic n by n random walk matrix associated to this graph. And then let me let A sub A be the matrix whose columns are the unit vectors of Mg with eigenvalue at least 1/2. Okay. And because G is a regular matrix or a regular graph, sorry, one of the eigenvalues or one of the eigenvectors is literally all one's vector. So without loss of generality, assume the first one is all one's vector. And then the isotropic spectral embedding or the spectral embedding is simply I take the rows of this matrix as my embedding. So each row corresponds to some node, right? There's n rows. So each one corresponds to some row. And this gives you some embedding of G. Okay, so if I just take the rows of this matrix, that is, and if I scale them by root n, it turns out that makes things isotropic, and we just call the scale version the isotropic spectral embedding. Okay. So now what I'm going to do is it turns out that my reduction is literally, I'm just going to take resilience over the uniform distribution over the isotropic spectral embedding. And in particular, sort of, you have these two key lemmas. I was hoping to prove the simple one because it's really like 5 minutes, but I'm not going to. But these really do say sort of, you know, expansion is closely tied to whether or not a small set has like a large deviation in norm. Particularly, the first lemma says that for every subset T, oh, and note that, sets, events of probability epsilon over the uniform distribution over these vectors literally corresponds to like, sets, subsets of size epsilon n. So the first lemma says that for every set, you have this following property, which is that the mean of this set, the alpha norm of this mean of the mean is at least sort of some quantity which is determined by 1/2 minus the expansion. So in particular, if I'm non-expanding, meaning that phi sub g is small of my set, then this quantity is large. So if I have a non-expanding set, this corresponds to a subset whose mean has large norm. Okay. So this says, non-expansion implies a non-resilient set because there's some set which is very far away. On the other hand, if I have all my sets are well expanding, so phi sub g is always large, then every set, the mean of every small subset is bounded. So it's upper bounded by this quantity, which is slightly nasty, but don't worry about it. But the point is, this is less or equal to, yeah. And this is sort of the connection, sort of somehow, small non-expanding sets directly correspond to like small subsets, which like shift the mean by a lot. I was going to prove this. This is like really like a very short calculation, but you know what? I'm going to skip it. It's like, okay. But that's sort of the high level idea, sort of why you might expect these things to come up. So now I'm going to talk very briefly about like how to try to get some reduction directly from robust mean estimation. We would like to try to use the same embedding. The problem is that robust mean estimation is like a promise problem. Namely that we need to guarantee that like there exists, like even in the case where there is a small non-expanding set, once you remove that set, the rest of the graph is well behaved. Or the rest of the distribution is like resilient or whatever. And this is just like not true under SSE as far as we know. So we're just going to assume it. This is, this is like, yeah, we're not complexity theorists. We can do whatever we want. So we're just going to say that if you're like, we're going to consider this more restricted class of graphs where there exists exactly one small non-expanding set. And we're going to consider this new assumption, which we call the unique small set expansion hypothesis, where this unique is unrelated to the unique games, but essentially it is still NP hard to like find the unique small non-expanding set. And under this hypothesis, we prove that robust mean estimation is hard. And as far as we know, again, the source of this is literally we asked Prasad, and he's like, yeah, it seems plausible. This is also probably hard, but we don't know. Okay. So that's pretty much it. There's lots of open directions here. I think this connection is really nice. In particular, like we didn't do any work. Like, our reduction is like super easy, right? Literally take this like standard thing, this isotropic or this spectral embedding, and just like say, hey, look, if it's like there's a small set, if there's like a small set expander, then it's resilient. Otherwise, it's not. So it's like supernatural connection. In general, I feel like there's more to be explored here. So one sort of more complexity theoretic direction, which really bothers me, is like the fact that the community sort of conflated these two non-equivalent hypotheses, but maybe that's not like my question to consider, another natural direction is just like, can we like prove robust mean estimation is hard from this more standard assumption, not like unique small set expansion or whatever we called it? And can you also prove hardness for other robust estimation tests? But like more generally speaking, just trying to understand this like very seemingly natural connection and like if there's actually anything more to it, because it does seem like there should be. That's it. Thanks.
All right, maybe we can take one question while Survey, I guess, sets up.
Yeah.
So for this, what problem we have?
So sort of like the same thing, like trying to beat 1 over root alpha under like better boundedness assumptions without like any
For
SOS.
that one, you can't prove a similar bound, right? So likely give the catch, maybe the sort of those kind of hypotheses.
That's the issue. But I guess the reason why that was something was because it there again there's like a variant of the SSE assumption, which in this time actually you can prove is exactly equivalent to SSE, which almost has this sort of like list decodable structure. So like there was like we felt like it was very close to actually getting some reduction there, but we didn't know how to prove it.
So you get a little omega of root epsilon, right?
Yeah.
But quantitatively, maybe the answer is much worse. Do you have any thoughts? We were saying between the root epsilon, right? Like epsilon to the 3/4, where there's a big gap. So it's somehow let's discuss of life.
I mean, we sort of show like the strongest hardness balance, like even improving on current results like constants is like hard. So shouldn't we get anything better is also probably hard.
Thank you. And all right, for our final talk, we'll have Serbi from